Good morning, everyone. I'm Marco Petri, and I'm here to present you Anomaly Detection in Quasi-Periodic Energy Consumption Data Series, a comparison of algorithms. This work is supported and funded by the European Commission in the context of the PRESET project. The PRESET project is a novel, edge-enabled, prescriptive and proactive framework for increased energy efficiency and well-being in residential buildings. There are 6 pilots, situated in 5 countries, with 70 households and 600 users. The project aims at making the transformation of the buildings from reactive to proactive more attractive to stakeholders, reliable, secure, cost-effective, and environmentally friendly. It also aims at enhancing the building energy performance and well-being, design and develop IoT and artificial intelligence processes, deliver procedures and algorithms enabling prescriptive maintenance, and provide advanced data visualization techniques to assist decision-making for optimized proactive building operation. Energy consumption, monitoring, and domotics are important to improve smart home sustainability. These tasks enable energy consumption reduction and prescriptive maintenance applications. We aim to use home appliances energy consumption data to perform early anomaly detection to avoid the device failure. And this task enables predictive and prescriptive maintenance. Therefore, the research scope is in the context of anomaly detection, which can be tackled with several algorithms spanning from statistical to deep learning ones. And although the anomaly detection literature is well developed, it still lacks a comparison of algorithms belonging to different families on quasi-periodic datasets. On the image on the right, we have an example of a quasi-periodic dataset. The 2 cycles are almost identical, whereas the third is quite different from the others in terms of shape. So it is not a periodic time series, it is quasi-periodic. So we want to pose questions and reply to them, and we pose 4 questions. How do algorithms compare in anomaly detection on quasi-periodic time series under multiple performance metrics? And we mainly used F1. For the algorithms that require training, what is the relationship between the length of the training and the performances? Again, measured with F1. For the algorithms that exploit window-based approach, for the prediction, what is the relationship between the length and the window and the performances? Last but not least, what is the generalization capability of the methods? How does performance degrade when a method is trained on one appliance and then it is tested on a different one? We reply to these questions by testing 12 algorithms with different parameterization on 3 different datasets. And the dataset we used are time series. So, temporal data composed of 1 or more variables aligned on the time axis. Variables could be either discrete or continuous, depending on the collection mechanism. We have univariate time series. On the imaging, you can see an example of the series we used. We have normal data and then 2 data that are considered anomalous and annotated with a tool that's called OldNTS. Anomaly detection, in general, can be performed on several fields, can be performed with univariate and multivariate time series, can be assessed with different performance metrics, such as F1, precision, recall, missile arm rate, and many others, and there are a lot of approaches to be used. The dataset we use is a time series about fridge energy consumption collected in Greek residential houses. The time series is spread over 2 months with 1 minute data resolution. Normal data of fridge energy consumption is composed of alternating on and off states in which the fridge consumes and does not consume energy. On the right, we have an imaging of these data. We have on states in which we consume slightly less than 100 watts, and off states in which we do not consume. The dataset has been divided in 3 sequences: training, validation, and testing, with lengths 1 month, 3 days, 1 month. And we use the method based on fast Fourier transform to find the dataset period for the 3 datasets, and we found 100 minutes, 80 minutes, 45 minutes. There are many methods to perform anomaly detection on time series, and all approaches to find what is an anomaly and how they classify an anomaly. So we can categorize methods based on how they do define and how they classify an anomaly. There are no systematic studies on how these algorithms perform on periodic time series and on their optimal parameterization. So we report the criteria used by the AD algorithms to identify and define anomalies, and we have chosen representative methods from each category. So, starting from definition, a method could provide a confidence, so a score for each point, representing how the point is anomalous, how much the point is anomalous. The method could provide the predicted or reconstructed value for a point, and then we compute the anomaly score as absolute or squared error. Likelihood, we predict each point n times, so being a point predicted n times, we can compute an error vector of dimension n, and we can estimate a Gaussian distribution of these errors, and we can use it to compute the likelihood of a point presented at test time. Malanobi's distance is similar to likelihood. We have that a point is predicted n times. We build an error vector, and then we use Malanobi's distance to compute the anomaly score. The last method is the window strategy. We have that data are projected on windows. Each window has one anomaly score, representing how much the window is anomalous. So, if a point is present in n windows, we build a score vector of dimension n, representing how much the point is anomalous. Then we detect an anomaly in 3 ways. Reconstruction error. If we have a method that aims at reconstructing a sequence in input, we base our anomaly score on the residual between the reconstructed and observed value. If we have a model that predicts point, we compute the prediction, we analyze the difference between the predicted value and the observed one. So the higher the residual, the higher the likelihood of being an anomaly. Last but not least, the similarity models. They classify points as anomalous or not by comparing them with the features or with the distribution of normal points, or by matching them with clusters computed from normal time series data during training. So we chose 12 methods: basic statistics, AR, ARIMA, so autoregressive and autoregressive integrated moving average, local outlier factor, one class as WEM, isolation forest, gated recurrent units, long short-term memory, these two with one-step prediction, the same but multi-step, so GRU multi-step, LSTM multi-step, and then autoencoders created with GRU and LSTMs. We selected these methods because they are representative of each category, and they are the most cited ones. For each of them, we have performed many experiments, varying the tuple training length, window size, and dataset. For training length, we use 2 weeks, 3 weeks, or 1 month. For window size, we use alpha period, 1 period, 2 period, 3 periods, and we do that on each dataset. So we have 3 training lengths, 4 periods, 3 datasets, and 12 methods. So 3 times 4 times 3 times 12, 422 experiments. Then we compare performance. How do the algorithms compare in terms of F1? Machine learning methods tend to have higher performance on average and lower standard deviation. And isolation forest has the highest performance. However, between the deep learning methods, LSTM and GRU models with multi-step prediction achieve low standard deviation without beating the machine learning performance. The single-step prediction models have lower performance, probably due to the high sampling frequency. The impact of the training length has been analyzed, and we observed that it's enough to train the model with 2 weeks. There is almost no difference in training the methods we have tested with 2, 3, or 1 month, 2, 3 weeks, or 1 month. We only attain a very slight average performance improvement with multi-step prediction models when we increase the training duration to a month. The window impact has a different behavior from machine learning and deep learning. Machine learning methods tend to decrease in performance when window size increases. Conversely, the deep learning methods increase in F1 when window size increases. Increasing the window over 2 periods can be counterproductive, however, for some methods, like the autoencoded ones, and generally provide slight performance improvement for other models. Last but not least, the generalization. We tested the generalization capabilities of the top 5 best performing methods. The isolation forest has the stronger generalization capabilities. We borrowed the concept of transfer learning and fine-tuning from deep learning. So we tested a model, training it on a different appliance, and we trained a model on one appliance. We found the best threshold on the validation of the testing dataset, and then we test it. On the bar plots on the right, the orange is training and testing on the same dataset. Green is training on a dataset, testing on another one. The blue is training on a dataset, fine-tune the threshold, and then test it. The generalization has revealed that isolation forest is the best again, and we have measured always the F1 metric. So, as conclusion, the machine learning methods outperform the deep learning methods in terms of F1 score. Isolation forest is the best performing method according to the same metric, the F1. 2 weeks of training are enough for most of the methods to provide good F1 scores. ARIMA and R models cannot train in reasonable time with high values of window size. Deep learning methods require longer window size, conversely the non-neural ones. And the best performing method in terms of generalization capability is again isolation forest. Further work will consist in trying different algorithms, trying different training, and trying ensembling techniques like majority voting, analysis of the runtime performance of the RD algorithms, so anomaly detection algorithms, on constrained devices in terms of memory and processing power. Then we aim at design an accurate and efficient system for dispatching mobile phone alerts about potential malfunctioning of home appliances. So, thank you for your attention.